Good afternoon. Welcome to CS Week's Marketplace. It's the third Tuesday at 2 p.m. Eastern webinar series. These webinars leading up to Conference 37 are the top-rated gold and platinum sponsors from Conference 36. I am John Sild, and I'm with CS Week, and I'll be your moderator today. CS Week and Conference 37 will be held from April 29th to May 3rd at the Tampa Convention Center, Tampa, Florida. Early registration is now open. This program will be recorded and available for playback, as are our other archive presentations found under the Educational Venues Third Tuesday link on our website. Today's program is Using Analytics and Distribution Automation to Realize Greater Smart Grid Benefits, presented by Kirkeby and Fred Behrmann. Attendees are encouraged to upload their questions in the Q&A panel, and please note to list them in the All Panelists. Your questions go to the All Panelists as they arise. However, all questions will be held until after the presentation for the Q&A segment. Introductions. First is Kirkeby. He is a Senior Electrical Engineer with Avista. Kirk holds a Bachelor's of Science degree in the Electrical Engineering field from Montana State University and a Master's in Engineering Management from Washington State University. He is a registered professional engineer in the state of Washington and has extensive experience in the electrical and gas utility industry. 6 years in substation design, 18 years in GIS, outage management, asset management, advanced metering systems, and engineering modeling, and 6 years in research and development. Mr. Kirkeby is currently responsible for applied research and development, focused on smart grid technologies. He also has a role of principal investigator for the Avista Smart Grid project in Pullman, Washington, which is a sub-project of the Department of Energy sponsored by Pacific Northwest Smart Grid demonstration led by Battelle. Our other presenter is Mr. Fred Behrmann. He is a Senior Product Manager for Itron. Mr. Behrmann is a Senior Product Manager at Itron whose responsibilities include the Active Smart Grid Analytics product line. He is a registered professional engineer in 4 states with over 25 years experience in the utility industry. Mr. Behrmann has focused the majority of his career providing design, consulting, service, and creating innovative software to enable optimization of transmission and distribution facilities throughout North America and around the world. Gentlemen, we thank you for joining us today.
Well, thank you. With that, we'll get started, and we're going to give you a little overview of the projects that are going on that require analytics, driving analytics at Avista using the Itron tools. And we'll give you a little bit around the business case, a little bit around the architecture, and then we'll get into how we're using the analytical tools to make decisions and plan for our smart grid rollouts to meet business objectives. So with that, let's get started. So a little bit about Avista. We're up in the northwest part of the country, northern Idaho and eastern Washington for our electric facilities, and then we have some gas down in southeast Oregon and northeast Oregon, southwest Oregon, in the Tahoe area and LeGrand. About 355,000 electric customers, 314,000 gas. So one of the things that we take pretty seriously is that we need to do analysis around both products, both gas and electric, because we believe that the right product for the right use should be promoted. So what are we doing at Avista? Well, when the ARA grants came out, we already had done quite a bit of research into smart grid and had proposed a project in Sandpoint, Idaho. That project was put on hold pending the outcome of our grant submittals, and we were fortunate to actually be involved in 3 different grants where we received funds from the DOE. First was our Smart Grid Investment Grant in Spokane, Washington, which is for 59 feeders and focuses on energy efficiency and reliability. The energy efficiency is distribution reliability, and distribution efficiency through voltage optimization, and reliability through automated restoration. Involves reconductoring and placing a number of primary switch devices along with cap banks and voltage regulators on those 59 feeders. Includes 110,000 customers of those 355,000 that we serve. Augmenting that particular approach down in Pullman is the Smart Grid Demonstration Project, which includes 13,000 customers. Here we're doing the same things that we are doing in Spokane with the addition of smart transformers, smart fault indicators, thermostats in customers' homes, and then a complete open way smart meter installation, with the idea that we would build on what we had done in Spokane and understand the incremental benefit to the additional equipment as to meeting business case objectives. And finally, we also got a Smart Grid workforce training grant, which was really key to retraining our workforce to be able to take advantage of the opportunity with this new equipment and to reset the skills and reset the job classifications for people appropriately. So getting into the Pullman project specifically, which is what we're going to focus on today, that's a 13-circuit, 3-substation, 13,000 electric customers, 5,000 gas customers. Once again, focus reliability and energy efficiency with the addition of customer experience, which is the smart meter and the thermostat used in combination to provide customer programs as well as to do a responsive program to a pricing signal. And you'll note again, I've highlighted that we have 5,000 gas customers. Those gas customers also have smart meters that get hourly interval data so we can understand the entire energy picture down there. So what is the business case, or the primary driver for the business case in this project? Well, for both projects, actually, the investment grant in Spokane and the demonstration project. It's primarily around voltage optimization, and we'll go into what voltage optimization is. And you can see the breakdown there. In Spokane, 83% of the business case for efficiency is in voltage optimization, with a little bit for pure capacitance additions and reconductoring. In Pullman, it's once again 78% voltage optimization with additional savings from caps and low-loss smart transformers. We have assumed through some previous studies, part of which was the Distribution Efficiency Initiative in 2007 conducted in the Northwest, that we should be able to get a 2-volt drop. And what does that equate to? Well, that 2-volt drop for these two areas is a 5.6 megawatt power plant, in essence. That's how much load and losses will be reduced with that 2-volt drop. So what are we really trying to achieve in a picture here? Well, voltage optimization, if we look at a normal feeder, we have a drop from the head end of the feeder to the opposite end of the feeder, where the last customer is served. And typically out of the substation, that voltage might be 126. So if you were one of the first houses out, you would be in that 126 volt range. If we go all the way out to the end of the feeder, it's going to be something less than that. In this case, somewhere around 117 volts. So that's a 9-volt drop from one end of the feeder to the other. Now, why is that? Well, part of the reason that there is such a drop involves reactive flow on the circuit, which basically is a need. You solve that by placing cap banks out there and bringing your power factor to unity. By doing that, by adding cap banks, I can flatten that curve. So basically now I've reduced that drop from 126 to 117 to 126 to approximately 122. So now I have a 4-volt drop end to end versus a 9-volt drop. So that enables me now to do yet another thing, which is bring that entire curve down. As I do that now, I still stay above 114, and I'm at about 118. So I still have that 4-volt drop, but I've reduced the entire curve. I've brought the entire curve down by, this is an exaggerated example, but 8 volts. So that would be 4 times my business case, so I would now be at 20 plus megawatts. That's not a realistic scenario, but just something to highlight for this voltage reduction and the impact that you can have, bringing that curve down. So what are our obligations? Well, we must serve in our tariff between 114 and 126 volts. So we don't want the meter socket voltage to be below 114, and we don't want it to be above 126. So those are the parameters within which we must work. And so let's, with that in mind, now let's take a little look at what we have out here to actually implement that on the system. So in Pullman, the engine, or the brain, if you will, is a distribution management system. And this distribution management system is using real-time power flow calculations. Now, a key thing about that is that for the real-time power flow calculation to be accurate, it needs meter data or load data at points on the feeder so that the allocation of load is appropriately done such that the accuracy for voltage calculations is correct. So here's where our smart transformers come into play. The smart transformers are streaming back kilowatts, kVARs, voltage, a loss of life, and temperature so that we have a complete understanding of load at all of the points on the feeder. We also have the smart meters now bringing us the same measures at the household level, but with control, of course, to connect or disconnect the meter, and with remote interrogation capability, alarms that tell us about events that have occurred on the meter. That's a very key thing that we'll get into here shortly. And we have cap banks, which are also controllable, bring back the kilowatts, kVARs, and voltage. So we've got those primary measures at multiple points on the feeder. And then we have smart switches out there that we've placed for our auto restoration scheme, and those involve control as well as those same voltage measures. So what we have is load at numerous places on the primary that if you aggregate all of the loads in between, they should add up. So that's one of the things we can do. We can add all the meters in between. They should add up to the aggregated points, which are the cap banks or the smart switches. So we've got a really nice double check to understand that our data is valid. And this data is all flowing in every 2 seconds with the exception of the smart meters. The alarms do come in real time, but the rest of that is coming in more like a 4-hour chunk. So we'll get into how that is relevant in just a minute. This is the typical configuration of one of our feeders. So you can see the recloser and the regulator in the station with cap banks out on the line. What you don't see is the smart switch that would be at the end of this connecting to the next feeder downstream. And then we've got the smart meters tied to the smart transformers, and you can see that what we're interested in here, because we're looking at voltage optimization, is the high voltage meters and the low voltage meters, here coded in a red and a blue. So we're going to be leveraging those devices to understand how to make the most of this voltage optimization scenario. So the first thing, as we estimated 2 volts drop, can we really get 2 volts of drop? So our first interest is in the planning phase to look at the actual circuit performance and understand if we really can get to where we want to be with our business case. So we can do that with the ASA tool, and you'll see that in a moment. We look at the voltage measure exceptions. So we're looking for those high measures and we're looking for those low. So that box voltage analysis is looking at those, filtering them to highlight the ones that are of serious nature to us. We then make a determination if they are or are not a problem. So if they're out of band or projected to be out of band, then we're going to have a problem, and we need to do something if we're going to have any opportunity to reduce voltage. So that might be, for example, going out and reconductoring a service, or changing out a transformer, or changing out a lateral. Whatever that might be, we have to determine that mitigation and to how many locations that mitigation must be applied. We bring that back into and calculate the savings, and then that, of course, goes into a business case, and the business case, of course, has all kinds of different logic depending on, in our case, there's very specific things around avoided cost of energy and cost of maintenance, et cetera. So at that point, we now look and have we met our hurdle rate, yes or no? If we haven't, then this feeder, and we'll do this feeder by feeder, then has no opportunity for savings. If the feeder, if it does meet the business case, then okay, the next step is to calibrate the savings. So what is the, where can we go precisely with our set point for the DMS? What that means is, what will our target voltage for that end of line be? What are we going to set that for? What is that target? So you can think of that as the planning phase, right? We are going to determine what the opportunity is and what it is that we need to do to mitigate problems to gain opportunity. Well, once we've determined that, now we can get more into an operational sense using this data. And we use the smart meter alarms for this particular circumstance, because it is what we can see in real time. We can still see all the end-of-line voltage measures, but what we're looking for is an instantaneous piece of information that tells us that we have a violation, say, of a tariff level. So you can think of these two pathways, the instantaneous and RMS, as being perhaps the instantaneous would be a violation of tariffs, so we've gone below 114, we've gone above 126. You can think of the RMS as more of a set point type of a value. So if we had targeted 116, for example, that indicates we have gone below the 116 level. So what we're trying to understand is our position with respect to our lower set point and our position with respect to tariff. Now, in the case of a instantaneous problem, which would be a tariff violation, we need to make a determination real quickly whether there's a problem with that meter that we can do something with, and then appropriately, if we can, adjust the set point. Both paths lead to that adjust set point, but the instantaneous is where we typically would have some kind of an issue with a particular meter that would require a work order. If the issues that we find with voltage are solvable, then everything's cool. We make our adjustment to the set point on the DMS for the feeder and move along. But if we can't solve the problem, our biggest concern is that we provide quality power to the customer. So we issue a halt to the IVVC, which IVVC stands for Integrated Volt Var Compensation, which we've recoined voltage optimization at Avista. That will issue a command to halt that procedure on the DMS for that particular feeder. And so this is a feedback loop, if you will, that we're headed towards. Now, currently the DMS doesn't do all of this, so we're working on this feedback loop to put it in a later phase of the project. And with that, now we're going to get into the actual tools that we're using from Itron to analyze this voltage. I'm going to have Fred talk a little bit about the tool sets.
All right, well, thank you, Curt, and thanks to the rest of you for joining us here today. As John mentioned, I'm Fred Behrmann. I'm the product manager at Itron for the Smart Grid Analytics suite of tools. So I thought I'd start a little bit with a high level to kind of put those in perspective, what we're doing there, and then we'll get into specifically a couple of them that Curt uses and the use cases that he just lined out with those flow charts earlier. So at the highest level, really, Itron's goals with the smart grid analytics, it's obviously to get more value out of your AMI system. Okay, now to do that, we've got a data warehouse scheme that goes in. We'll take all the AMI data. We'll also take from a variety of other sources, SCADA data for some of these upstream devices that Curt was talking about, whether they're smart transformers or you know, smart devices, switches, or right at the feeder. Another good source is GIS for how they're connected. That's how we know which meters are all on one feeder and their locations on the feeders and laterals and those sorts of things. But the idea basically is to take all this data and crunch all the numbers, do some heavy-duty analytics, and then present that out to the user in a variety of user interfaces. And we'll see a couple of them here today. And the whole idea is, of course, to get actionable results. Use this data to provide actionable analytics, which is what we all hear about. That's how you're going to go and operate your system. Where Itron is focused primarily is in the three areas I've got listed on the screen there right now. Power quality, energy diversion, which is kind of a euphemism for theft, and transformer load management. The idea here is that Itron, we're really focusing on delivery analytics. We provide customer presentation and that sort of thing as well, but our real focus with the smart grid analytics is optimal delivery of energy and water. And that kind of follows in these things here, whether it's with the power quality issues, driving down the technical losses, or, you know, the non-technical losses that are sometimes referred, basically leaks, theft, those sorts of things. Transformer load management really is in an asset management type thing, keeping tabs on the loading of your transformers. We're not going to go into many of those today, but we will specifically look at power quality analytics and the way Curt and Avista are using them. This is a real broad subject, and a lot of things could fall into power quality, but what we're currently doing in that area is the voltage monitoring. In this new world of AMI, it's really fantastic. We're essentially measuring the voltage at the delivery, every single delivery point. In Avista's case, actually, it's obviously real time going on and reporting back 5-minute intervals. Allows us to spot these exceptions and trends and things. Similarly, what we're going to spend even more time on today really is this feeder voltage profile, because that is, Curt had a few diagrams earlier of that's your voltage at every service point on the feeder. And first, in identifying potential feeders for savings, and then after you've identified those and implemented something, how you're actually operating those and to see that they're working as designed. A couple other areas that we won't go into much detail, but outage reporting, of course, we also know, when every meter goes out and back on in the system, that we can learn a whole bunch about that, or persistent outages, things like that, as well as tying in with outage management systems and things. Transformer load management, we may, if time allows, we can show a couple of shots of how we do that, but it's basically aggregating to the transformer, running some fairly simple compare your KVA to the nameplate rating, and some more sophisticated loss of life calculations based on the IEEE sort of standards that really take into account weather and duration of loading, things like that. Anyway, so that's just kind of an overview of kind of what we're doing at Itron, and we'll spend most of the rest of the time really looking at two of these, basically voltage, conservation voltage reduction and voltage optimization. It's all about voltage. So these are a couple different views, and I'll just briefly give you kind of a layout of the screen. Curt's going to go into detail of how he uses it, but to get a basic overview of what we're trying to look at with this dashboard, we're taking a lot of really complicated ideas and trying to make them as simple as we can. A lot of times people kind of overdo it with the dashboards, and too many bells and whistles are a little bit counterproductive. Here we're trying to boil it down to really the simplest view on a feeder you can, and still give you the tools to drill in and learn what you need to. So in general here, we're looking at a slice of time. In this particular case, we're looking at a month back in April. Those are set at the top. The upper left-hand quadrant is, what do we have, about 8 or 9 feeders there that we're interested in. And that's the voltage bounds, or the voltage operating band that these feeders have seen. So in this month's time frame, what's the lowest voltage measured at any service point on the feeder, and the highest voltage? Okay. Right about in the middle there is right at nominal voltage. So we're varying, some of these feeders are going between about nominal voltage up to about 5% above. that's right, and that's real good operating right about your tariff. Some of them are dipping down lower to about 3 or 4, even 5% below nominal, which is the ones we're going to take a look at. But so that gives you, just at a glance, you can see how these things are operating. This is at a month. This could be for a day. It could be for a week. It could be even for 1 5-minute interval to just see how your voltage trends across your feeder. And for the selected feeder up top, in the lower left-hand quadrant, that's the distribution of your highest voltages and your lowest voltages for every service point. Kind of a histogram, but we're doing it in a line graph just because an overlapping histogram is kind of hard to look at. But that's just your distribution of voltage along each feeder. On the right-hand side, we've got a map that's showing you, where your higher or low voltage type things are occurring. There's a slider down at the bottom that Curt will demonstrate here in a minute to see, the distribution of your low voltages, whether they're technically low or not. They're your lower voltage, maybe 3 or 4% below nominal. You can see where those are because you'll find as they cluster, they may all be out on the end of a feeder. They may all be at one transformer. Those can shed some light on how you want to solve those voltage issues, which then gives you a lot more room to move with your CVR. So that's enough of a general overview, Curt. I'll turn it back over to how you use it.
Okay, so that said, when we take a look at those feeder bars in the upper left, you can see the ones that are shorter have immediately have some opportunity for voltage reduction because of where they're placed and because of the narrow nature of that band. As we get into the ones that have a longer appearance, such as this feeder, you can see by both the length of that line that there are high and low voltage distribution that's more distributed, and you can also see now how far apart they are in the curves in the lower left. So we like that the curves are fairly narrow, but the high and low are separated far enough that this feeder might have some difficulty being reduced. So what we really want to do is take a look at this particular feeder and see if we can determine the nature of these particular voltage elements. Is it a few meters? Is it a bunch of meters? Is this a problematic feeder? Is it just problematic services? So we're going to try and characterize what the mitigation might be for this particular feeder. So if you can see there, I slid the bar down on the lower right down by 1%, and now you can see some red meters show up, which indicates that those meters are all above that particular set point, which is, I believe, 4%. So now let's slide that back up, but also bring our lower. We're interested in the low voltage primarily, so as I bring that up by 1%, I can see that I did get a blue dot there in the map. And let's take and zoom in on that map a little bit. As I slide it up another 0.5%, I've now got 3 meters. So I happen to know that that this is all 3 services off of the same transformer. So immediately I suspect I may have an issue with the transformer, possibly, instead of a problem with the meters, but I need to validate that. So what I'm going to do is take a look at that first service point. So if we go back, it was the middle service point that was the lowest. So now let's take a look, and we can see the parameters around that particular one, and we can see that the low voltage was 112.8, and that is, below our tariff. So that's not good. We really don't want to see that at all. So we're going to have to do something with this particular meter. So to do that, though, we need to understand what exactly is happening with that. So we're going to switch over now and take a look at the service point itself. So we now switch to a different module, if you will, or a different dashboard within the tool that is giving us a little bit different look now. In the upper left corner, we have the most serious offenders of high and low voltage. The one highlighted in yellow is the one that is showing in red on the screen on the map in the upper right corner. The lower right corner now is showing us a graph hour by hour for that particular day that the event occurred in. And we can, the nice thing here is, so we get a good feel for where we are with that particular point for a period of time. So I just slid it ahead a day and another day. So I can see that I've got a number of dips right below my low point, my tariff level. So I really need to understand now what's happening here. So let's take a close look in a report. So we jump out of the dashboard into a report, and this curve really was what you were just looking at over time that gives the voltage and the load. So the red line is the load, the blue line is the voltage. And you can see as the load increases, the voltage drops. So right off the bat, as an engineer, I look at this and say, okay, well, that makes sense. But I also look at it and I wonder, okay, what's really going on? Because I'm not sure that those dips are actually as far down as what that said on the screen. It said 112.8. It doesn't appear to me that it's that low. So let's go in and get a little more granularity. So here's a 15-minute graph, and you can now see much better what's actually going on with respect to both load and voltage, and you get a more precise measure of the voltage and how long it was at that particular voltage. So I can see that I've got a couple of places here where we have some issues with that voltage that occurred over more than just a single 15-minute interval. But you can also see that now I'm not averaged over 60 minutes, so I get a fairly good view of what's really going on. Now I have 5-minute interval data on all these meters, so let's take a look at the 5-minute. In 5-minute, it doesn't really buy us a lot more information, as you can see. So this is one of those business case learnings that what should be our interval as we set meters across the entire service territory. Is 5-minute valuable? Is 15-minute valuable for each particular use case? Now, in this particular use case, it appears that that 15-minute was adequate to determine I really had a potential problem. So, popping back out to that, what we're doing is really trying to analyze that particular point there that's in red and understand where the potential is for fixing it. And I still remember I had that transformer thing going, right? I know that I could go look at the transformer. So why don't I do that? So those three services, and there was actually another service involved, are served off of one transformer. And here I can see that actually there were events, low voltage events, on all 4 services that were on that transformer. And you can see the listing of the events down below. So that tells me that, okay, it certainly is that transformer with loads. Maybe I should look at the individual loads rather than the aggregate. So now we take a look at a graph that shows each one of the individual service points and also shows the voltages for each one of those. So the voltages are in red, the loads are in blue, and it's clear from this graph that I have one service off of this transformer that is driving most of the voltage dip in the rest of the services as an aggregate. You can see the light blue is substantially larger load and got much more spike to it than any of the other loads. So my natural reaction to this would be to either take this customer and put them on their own transformer, or to take a close look at their service wire and understand if perhaps there's some kind of an issue between the transformer and their meter, or even downstream of the meter into their load. This probably is something more like a small commercial on with some residential loads, and so here I can actually mitigate the circumstance which might prevent me from lowering the voltage on this particular feeder. So this is what we're really after, to determine that potential and to be able to mitigate the possibilities that are limiting us with equipment and installation issues. So once again, here's how we walk through that. What we just did with the analytics is we took a look at those voltage measures and exceptions. We did the voltage analysis to understand where those low and high events were. We determined whether they were or weren't a real issue, and then we determined if there was a mitigation path. Calculated our savings. You didn't see that part, but we would calculate the savings, apply it to the business case, and determine if we could or could not lower the voltage, and if so, calibrate our curve based on those voltages. With that, I'll let Fred talk a little bit about transformer load management.
All right. Well, thanks again, Curt. It looks like we've got about 8 minutes left here or so, so we can go into another module. They're using this in Avista as well in kind of a different sort of scenario, and in this one it's real interesting as well because Curt mentioned they have the smart transformers down there, which are actually have the meters on them. We can compare our aggregated analysis to the results of those for some real interesting analytics, I think. Not all of them have that. It's a subset, about 1/3 or so down there are having those, and we'll really prove out the validity of those as well. So interesting, those kind of going on in parallel. But as our basic transformer load management or transformer evaluation software is built around aggregating the service points loads to the transformer. That connectivity would be provided from either GIS or sometimes an outage management system, but just basically this is a good example of providing just a little bit more information can provide a lot more analytics. So if you provide that connectivity, just essentially that these 6 service points are on this one transformer, that one transformer maybe is a 25 kVA overhead transformer that we have some curves, or you can even put your own parameters in. We can then calculate the loading on those in quite a bit of detail. Again, just checking with your maximum kVA usage over the rated nameplate, which is a valid but sort of simplistic way of looking at it. You can look at that in conjunction with your loss of life calculations, which actually, as I mentioned before, take into account the ambient weather and the duration. It's heat that breaks these things down, of course, so if it's just a spike that's up for 5-10 minutes or even an hour or something on a cold day, not nearly as bad as something that ramps up, stays heavily utilized all day long, day after day. Okay, so the results of those, once again, we put into a relatively simple dashboard here. 2 real ways to look at this in transformer loading. This particular dashboard is laid out to show me my worst offenders. So if I'm responsible for, managing these assets in this particular service territory, show me which ones are the worst. You can go into this dashboard. Of course, we have all sorts of reports that can be initiated with emails or weekly reports or anything like that when there are violations that occur. The dashboard, of course, is the easiest way to show you what we're doing in a presentation like this. But basically, show me the worst case based on just kVA rating or the loss of life calculations of those transformers. We again provide the tools to dig in and see just exactly what's happening. Okay, just because it did see 125% of its nameplate rating, is that really a problem? I can drill into a lot of these details here and go in and see, well, it's only happening every once in a while. This particular graph, by the way, is kVA in blue with the ambient temperature in red, ambient being the temperature outside when it saw that peak loading. But I can drill down in and see a little bit, how bad the loading really is. So again, this is kind of a look. So if I've got budget to replace 20 transformers, which ones should they be? We can also look at them, underutilized ones, but that it's usually a little bit tough to justify replacing an underutilized transformer, unless maybe it's a big, 1500 kVA pad mount transformer that, all the commercial has moved away from that particular place and it's sitting there about 10% utilized while you're buying another one for top dollar to go put out in a new business park or something. There are cases like that where you can definitely get a lot of value out of those more or less stranded assets there. But in general, these are, you see where this can really show you, you know, electric vehicle adoption and things like that. They're going to start to show up on these things, and hopefully you can, you'll notice them and see the trend prior to, you know, burning up the transformers and losing those assets. Another way to look at this, and this is where some of the dials are in the bottom. We got a different dashboard, but I don't have a screenshot because it's so similar. But in the situation of a staking engineer or something is adding another home to a transformer, well, if I've got, you know, 3 or 4 years of history or even a year's worth of history on this transformer and knowing exactly what the loading is, I don't have to depend so much on a standards with, you know, assumed residential loading and diversity factors and things like that. I said, well, exactly what's this thing been experiencing for the last couple of years, and what is another 5, 6, 7 kVA, you know, estimated load going to do to it, so I can really optimize that transformer, you know, size that for the proposed new service. Similarly, you know, a car pole accident or something, you just take the same transformer out there in the middle of the night. Well, you can actually get something like this in the hands of the warehouseman or the line foreman and say, okay, hey, you know, this is the perfect time to upgrade that transformer. Let's get it sized right while we're here. So in that particular dashboard, they type in an account number or a transformer ID and actually get this same sort of information, and they can add additional load or whatever with some of these, some of the minor inputs down in the lower left-hand side there, and really get the right size transformer based on your criteria that you want to apply down in that additional loading. What I really like about this piece, though, actually, is in looking for ways to drive more and more value out of AMI systems. This is the case where you're really getting the results of the AMI data in the hands of a whole different set of people that you wouldn't really think are getting value from that. We're all starting to see the value in crunching these numbers in the back. You got some back office guys crunching through these numbers and finding all sorts of amazing things. But this is really an example of getting that out in the hands of more and more people and just driving more and more value there. A couple other things I mentioned, we kind of can drill in from these dashboards, and like Curt did, to go in. You've got this wealth of information that's really just right behind the scenes here. The idea of the dashboards is really to point you at the anomalies in your system, you know, the outliers and the things, you know, because most of the time, 90%, 98% of your system, everything's functioning real well. You've got these outliers. You find them with the dashboards, and then we provide the tools to go in and really see what's happening, as Curt drilled all the way down to individual voltage measurements at all the services on a transformer for a couple of days that were causing trouble. Similar with transformer loading, this is a graph I just had up there, but it shows the history over time. This could go back years, or it could go back to last winter or last summer, whatever your peak is, and look that way. And all sorts of different things from a supervisor level is what is the distribution of my loading, what are my worst loaded transformers. These types of reports could just show up monthly, weekly, yearly, whatever you want to do to just kind of see how you're utilizing those assets. Because again, you got a lot wrapped up in transformers. If you treat them right, you know, you might get 40, 50 years out of them. If you don't, you won't. So anyway, just wanted to kind of touch on another type of analytics that we're doing down in Pullman and elsewhere. And I don't know if you had anything to add on the transformer loading, Curt, or as far as wrapping up.
I think I'll just wrap up with the analytics that we're conducting on these projects is absolutely critical to A, validating a business case, or even prior to that, generating the business case, but B, validating the business case, and eliminating work. So all of these things that we showed you, we intend over time to make them automatic, to make them do work for us, to generate work orders automatically, so that our engineer time is spent on the real trouble aspects, or on the need to review design standards, or on the need to review installation methodologies, whatever that might be. So we see this as one of the most critical results that could come out of, or methodologies that could come out of our smart grid projects, that this should drive business value in a number of areas. And we're really excited to be working with Itron on these analytics and be able to really leverage them to the degree that we believe we can. And with that said, I think we'll conclude and take questions.
All right. Well, good job, Curt and Fred, both of you. Thank you for your informative presentation. It was well done. And so I do have a couple of questions that have come through. The first one is going to go to Curt. You mentioned you are reading AMI in 5-minute intervals for the Pullman project. How much value does that provide compared to an hourly reading?
Well, that's a good question, and we wanted 1 minute, but we decided that might be a little bit of overkill with new systems that we didn't understand real well, and that was a good decision not to go with 1 minute. But 5 provides us, as you saw, it might not be as productive as it looks in voltage, but we're also trying to understand on our customer side of things, we're trying to understand the load that a customer has and to actually give them actionable items at their particular residence or business that would allow them to reduce energy consumption. So that's where we really wanted to be at 1 minute, because we can get a really good understanding of what's happening in that location. But 5 minute is actually giving us a very good ability to predict forward what the customer might expect for a bill, or even what they might be able to do to hit a target. So we find a lot of value so far in the 5-minute intervals.
Gotcha. Okay.
I had one thing if
go
I
ahead.
could add
to
that, John. And I think that is a good question, because it's a balance that you're always having to do. You know, certain things are fine with hourly, other things you want to get even less than a minute. You want to be down to a second less. And that's just not practical with the quantities of data and all. And so it's something that customers are always wrestling with. At Itron, we are as well. Always looking at ways that we can get the value of the real instantaneous sort of measures when you need them. But as we mentioned earlier, you don't need them all the time, right? So certain things, I want to really know that amount. The rest of them, I don't really care. So we're always putting, it's kind of an advantage with Itron, building the meters, building the collection system, the meter data management system, the analytics. We can put those features where they do the most good. So certain things we can trigger at the meter to start recording. We can do different things with analytics, with driving different intervals based on what you need, based on the outcome of the analytics and those sorts of things. So hopefully we can keep it at practical levels, but still get the sort of granularity that a bunch of us engineers really want on the instantaneous level. So that's all I had to add.
Okay. All right. The second question I have for you guys, in what way will you be able to validate the energy savings?
Okay. Well, that is the holy grail, in that if we're going to spend customer money, shareholder money on solutions, we should be getting the return that we expect. And then in addition, we have mandates from regulatory bodies that say thou shalt collect savings, energy savings, and you will validate them for us so that we understand you got them. So we have pressure for the business case itself, and we have pressure from the regulatory bodies. So this is a very key element especially of distribution efficiency. And it's there's no holy grail for it today. Most of it involves a day on, day off type of a scenario, with the Protocol 1 standard being 60 days off each season, which would mean your system would be off 240 days, leaving only 125 to actually operate. That's not very effective. So what we're doing at Avista is we're working with the Washington State University to develop a methodology that could understand the load makeup for every 5, 15, we're not sure on the interval yet, 5, 15, 30-minute interval, and determine the savings for that interval based on load flows for the actual measured and then load flows given the prior settings. And so we're working on that methodology right now, and hope that and it looks very good, that will provide the kind of results we want and allow us to have a methodology that is acknowledged as accurate, so that there's no ambiguity around the results.
Okay. Next question. What are the primary drivers for voltage optimization, and what about revenue loss?
So I just named really the two drivers, which are the business case to gain energy back, if you will, and then the regulatory concern in the RFP standards to renewable portfolio standards to really reduce consumption. So the lost revenue question is one of those that pops up in utilities quite often, and if you're an engineer, you can recall back to GE's omnibus book for voltage regulators, which indicated that we should set the voltage as high as possible for maximum revenue. So what we're doing is obviously the opposite direction. We're lowering voltage, which will reduces losses, but primarily it reduces load at the customer. So that's a really good question. How do you mitigate that? Well, there's a number of ways. One might be with regulatory, protection, so revenue protection at the regulatory level. But we're also looking at other ways that we might want to manage that kind of a system. If you have the ability to adjust load, which is really what you're doing, might that be a formula for ancillary service management if you had it across the entire system, which would end up reducing the cost of ancillary power dramatically, and might actually be more savings than you'd get from just a drop in of 1 or 2% at the customer load. So it's a balancing act between the different competing costs that you have and how you may operate the system. And I can tell you we're in the middle of those discussions on how, in the long term, we might want to position it. And of course, there's always it's like a power plant. So if you can sell the power somewhere, and if you have the ability to add load, then you have that power plant built in. So it's a tough question. Every utility has to answer it for their own operation.
Okay, very good. All right, another question that has come in. Where do you see the analytics being utilized within the organization, and by whom?
Well, I think that's, for us, that is primarily in the engineering area, in the planning folks, and in the automation realm. So the automation people want to know how to set the system up. Planning people want to know what the opportunity is and where those set points are. Then I guess there's even the third body, which is really the people responsible for the integrated resource plan, because they also want to know what the reality is around that resource. So I think it's those three particular bodies, and then as I said, as we automate things in the future, there will be less review from those folks, just focused on trouble, which perhaps might shift down to our designers.
Okay. All right. Well, we're nearing the top of the hour, and we want to be respectful of your time and everyone that is on this webinar. So we want to conclude promptly. If your question was not answered during this time period, we will forward that question to our presenters, and they will be getting back with you after the webinar. This will now conclude our webinar, and we thank you for attending.